Hello Year 13 chemists, welcome to TP's Chemistry Cuts. In this clip we'll be looking at identifying all the species in a given solution and then placing them in order of increasing concentration.
Okay, so we're going to be looking at species in solution because it's really important you have an understanding of what the relative concentration of everything in solution is when we start looking at reactions involving particularly weak acids and bases, okay? And their relative concentrations will be very important, as you'll see. So what we're going to do is look at a series of different types of solutions and then order everything in terms of what's the most concentrated to what's the least concentrated, having worked out what reactions are actually going on in solution. So as a starting point, we need to be very clear of what actually happens when something dissolves into solution. The whole of this course is based around solutions, and so you have to understand that initially you've got your pure substances. The solute is the thing that dissolves in the solvent. The solute particles, when it's pure and before it enters into solution, are packed together closely, either as a solid or as a liquid. So solids could be either solids or liquids. And when you mix the solid or liquid solute into the solvent, which in our case is always going to be water, then those particles from the solute separate from one another. That's the first thing we need. And they become separate and get surrounded by solvent molecules. So that's what that's all about. After that, the particles may or may not react. Some do, some don't. It's not a fixed rule that everything does react, as you will see. And part of the course has been about whether some things react completely or not. So let's start simple by looking at strong acids and bases. Okay. Now strong bases are basically metal hydroxide salts, all of them. Okay. So, and those are all solids initially. So the first thing you need to do is make a solution of them. So you've got to add the solid into solution, and that's what this equation shows you. You should always write a dissolving equation in terms of what you start with its phase. So in our case, obviously it's a solid, but it might be a liquid if we were looking at something like ethanol or something. Okay, and put H2O over the arrow. Okay, and a dissolving process here to make the solution is a one-way thing. We're not setting up an equilibrium when we're looking at it in this context. And so you then separate the particles, which in this case are ions, because we have a mixture of metals and non-metals, and that's our starting point. Now we know that sodium hydroxide is a strong base, so sodium plus is the conjugate acid of that strong base. From last year and earlier in this course, we know that the conjugate acid of a strong base is unreactive towards water. That, in fact, is the reason why this is a one-way reaction. You get complete dissociation. There's no reassociation because the sodium plus prevents that. Okay, so that's the formation of the solution. The other thing we have to be aware of, because we've got to be aware of everything that's going on in solution, and water itself is an amphiprotic substance, so it auto-dissociates. One molecule can act as an acid, one molecule can act as a base, and so you get this auto-dissociation. What we need to do, that's about it. There's nothing else happening in that solution. So what we need to do now is look at all the species there and look at their relative concentrations. So what I'm going to do for each of the things we look at this lesson is consider 0.1 mole per litre solutions. Okay, now, it's possible that some of the things may not form a 0.1, but we'll just pretend they do. Okay? And we'll look at everything in relative context to that. So if we're making a 0.1 mole per litre solution of sodium hydroxide, we get 0.1 mole per litre with respect to sodium, plus 0.1 mole per litre with respect to the hydroxide. In that solution, the water will be at 55 point, I put 5.5 there, it's about 55.6 in fact. And if we look at the auto-dissociation of water, what we get is 10 to the minus 7. So that's 1/10 millionth of a mole of A3O plus and 1/10 millionth of a mole of hydroxide. Okay, so these are tiny, tiny. So when we come to put everything in order, always the first and most concentrated particle in an aqueous solution is going to be water itself. Okay, and that's always going to be very much more concentrated than anything else. Now, if you get a question on this, and they do come up occasionally in the external exam, they'll often say, don't include water. If they do that, please don't include it, because they'll mark you down if you do. Okay, so don't get into this rote habit of always putting water if they're not asking for it. Anyway, so this is always going to be first, and then we need to look at this side of the board. What I've done is I've put things up in decreasing concentration, and you'll get into the habit of doing this if you follow what I do today. So we've got 0.1 mole of this and 0.1 mole of this. But you've got to be really, really careful, because there's this other one, and this also adds on to that. So there's two reactions that give rise to OH minus, so you get a little bit extra. But when you consider the size of that and that, when you add them together, in terms of the significance, it stays much the same. It's still about 0.1. So what I've done is I've said that sodium is the next highest, and it's about the same. There's no real significant difference between them, but this one here is slightly greater, possibly. Yeah. And then the only thing we've got left over is H3O+. Don't ever forget the H3O+, because otherwise we wouldn't be able to measure a pH. Okay? But there's also something you've got to be aware of, and this is one of those things that causes all those issues when you're doing those KS calculations, is some salts are not just one-to-one. So when you form a 0.1 mole per litre solution of it, the concentration of one of the ions is actually greater than 0.1. So the example I've given here is calcium hydroxide. So if you dissolve that up to make a 0.1 mole per litre solution of calcium hydroxide, for every one of these, I get one of those and two of those. So I get 2 mole per litre, also 0.2 mole per litre of hydroxide when I've got 0.1 mole per litre of calcium. It's so easy to miss that. Okay. So if we now order it, going from this side, we start with H2O as our highest concentration. Then we've got these. What am I doing here? We're ordering it in terms of this side. These two are going to be the two highest concentrations, but this is double that. So there's no approximately equal to. So we've got hydroxide is the next highest, and then calcium 2+. So you need to be careful that you look at the ratio of ions in the salt before you start ordering everything. Okay, moving on to strong acids. My OCD means I haven't done that, and I need to do that, of course. These are, by definition, things that completely dissociate when you add them to water. So if you take hydrogen chloride, which is a gas, and add it to water, the hydrogen chloride molecules completely dissociate, and you form a 0.1 mole per litre solution of H3O+ with a 0.1 mole per litre solution of Cl-. So those are our highest concentration things in solution. And then we have this second auto-dissociation of water reaction going on. And then if we just look at our concentrations relative and plug them in here, we start with water as our highest, then hydronium, which is going to be very, very slightly greater than the chloride because there's two reactions that produce it, but the significance of this one is very, very slight, so overall they're approximately the same, and that's what you should write in the end of your exam. Okay, and then you've got OH down here. So you can see that when we start to look at weak acids and bases, things are a little bit more complicated. And the reason is because there are two types of each. For each one, you can have either neutral molecules, which are themselves straightforward dissociation into the conjugate acid plus its plus the OH minus. But also, you can also get something that is a weak base that's been formed by the neutralization of a weak acid. Remember, the weak acid, when you neutralize it, forms into its conjugate base. So, giving you two examples here, if you look at the standard one is ammonia, neutral molecule, then that dissociates partially in water, it's a weak base, and you get ammonium, which is the conjugate acid of that weak base plus OH minus. And you'll notice I've ordered them exactly as before, starting with the the adding of the molecule to water to make it into the solution, then any reaction that occurs later, okay? And there is none in this case. Okay? The actual adding in it is the reaction itself. So, if we look at this side, we know we start with water, so we've got ammonium and hydroxide, and although hydroxide appears in this one, again it's not significant in terms of the quantity here for a 0.1 mole per litre solution. This is 10 to the minus 7, so those add to give basically 0.1 mole per litre. So these two are approximately the same. There's the next biggest one, and the only thing that's left over now is H3O+, which is very much lower in concentration, but it is significant because we can measure pH using it. As I say, you can also get a salt when you neutralise a weak acid. So if you take, say, hydrofluoric acid, which is a weak acid, and you add a mole equivalent of sodium hydroxide, you'll get sodium fluoride in solution. Okay? And you take the water off and you've got yourself a nice crystalline solid there. So if you take that sodium fluoride and dissolve it up, then you've got sodium and fluoride ions, 1 to 1. Okay? And then sodium we can ignore for the moment. It doesn't react with water because that's the conjugate acid of a strong base, so it doesn't react with water, so it's not going to do anything else. But this is the conjugate base of a weak acid, and that does react with water, so we have to write out an equation for it. Okay? And so it accepts a proton from water and forms HF and OH minus. Okay? And then we've got the auto-dissociation reaction. Now we've got to put everything in solution in order of decreasing concentration. And this is the way I always write things. I do things that the first dissolving, then the next reaction from one of these species, and then the auto-dissociation at the very bottom. You need to have everything on this side in your ordering of species in solution, because all of those are in solution. Start at the top. Okay? So we've got water, which we would take as said, because it's an aqueous solution, so it's always going to be the greatest. We've got sodium and fluoride. Okay? Those are approximately the same. Even though some of this gets taken away, it's a weak base, so it's only a very small amount that dissociates, or associates in this case, and so the change in concentration due to that weak base behaviour is going to be very, very small. In terms of the significance of the numbers we're dealing with, it's not going to be that significant, but once again, put an approximately equal to the concentration of fluoride. Okay, so that's dealt with those two. Now we've got these two. Now this one's going to be slightly greater than that one because it's two reactions that produce it. So I'll put OH minus next. And that's going to be approximately the same as HF. And then left over is this one. And now I've accounted for everything on that side. So as you say, it's a little bit more involved when you go from this one to this one because you've got extra species to put in. But if you lay it out like this, then you can sort of use a pencil and just check them off as you go. So similarly with weak acids, you can have neutral molecule ones, and again it's the same as all the other things before. You just do the addition to water, and it dissociates partially to give the conjugate base plus H3O+. There is no other reaction in the water other than the auto-dissociation. Okay, so relatively straightforward. Start at the top. We start with water anyway. Then we've got these two approximately the same, although the OH or the H3O+ is occurring in two reactions, so it would be slightly higher, but put the approximately. In fact, it might be a bit more logical to put the H3O+ and first, and that one makes not that it matters. And then left over is OH minus, which is in a tiny amount compared to everything else. Similarly, With the salts of a conjugate acid from a weak base, you've got a little bit more involved. So if you were to take, for example, the weak base ammonia and neutralise it with HCl, you'd get ammonium chloride. You can get that as a nice white crystalline solid. If you dissolve that up, you've got these two things in solution. The conjugate base of the strong acid is unreactive, so you can forget that now. That's just going to float around as is. But the conjugate acid of NH3, or in this NH3 in this case, but the conjugate acid of the weak base is going to react with water. So you get this second reaction going on, okay, between the conjugate acid and water to form NH3 and H3O+, and then you've got the auto dissociation of water. So if we look at everything on this side, okay, so start off with water. The next thing is NH4. Now a little bit of that's going to be taken away, but not a significant amount. So that's approximately the same as Cl-. So I've checked those two off. Okay. Now I've got NH3 and H3O+, but H3O+ will be a little bit greater because it's produced in two reactions, but it's not significant. So that would be about the same as NH3, and then left over is OH-.